have to some exponent. And we just go through the letters. Yep.
How does the reaction rate decrease as the reaction proceeds?
Well, as the reaction proceeds, you're getting products. These products are getting in the way of the reactant particles colliding. So it's like, let's say I send this class down the hallway. Now, you'll be able to get there a lot easier than if the bell goes and I ask you to go down to the end of the hallway when all the other students are in the hall. Right? They get in the way of the reaction. So the products get in the way. So instead of colliding with another reactant, they collide with a product. So K is temperature dependent. So most of the questions, if they're written properly, will give you a temperature at which the reaction occurred. You don't have to do anything with that temperature. It's just how we state the question. It will change. It will change during the reaction if the temperature changes. Otherwise, it is constant. It's the rate law constant, so it's constant at that temperature. If you change the temperature, your K will change. It also tells you something about your rate. If it's a large number, it means it's a fast reaction. If it's a small number, it's a slow reaction. So, and we're going to figure out K values. And this, remember I said you're going to get some weird units in this kinetics unit? It's going to be for K. We're going to get some very bizarre units, and that's okay. So, if we get an exponent, 0, we say it's 0 order with respect to the reactant. If it's 1, we say it's first order with respect to that reactant. 2 is second order, and so on. So if you have an exponent 2, don't say a to the 1. Say first order with respect to a. And then the overall order for the reaction will be the sum of your exponents. So it could be third order overall because you had an exponent 1 and 2, or a 1, 1, and 1. So we talked about that as well. I'll get into the... Okay. What number do you associate with doubling? 2. So if I say the rate doubles, we're talking about a factor of 2. If I say the concentration doubles, a factor of 2. So if I double, so if rate varies with the concentration, and I say we double the concentration, and the rate change is the same. I doubled the concentration, but the rate did not change. What would be my exponent? 0. Yeah. What is any number to the exponent 0? 1. So if I said we doubled the concentration and the rate changed 4 times faster, what would the exponent be? 2. If it was 3, it would be 8 times faster. 2 to that exponent gives you 4. 2 to 2 is 4. And if I said we double it and the rate doubles, what is it if I double the concentration and the rate doubles as well? It's order 1, yeah, first order, okay? So this is what we're going to do. We're going to take data, and we're going to figure out what our exponents are, what our rate laws are, and then figure out what our so when it says write the rate expression using exponents, that is R is equal to K. Then you put in your reactant to some exponent. Usually we use M and N. So that's the rate law expression before we figure out what the M is and the K is. So then we want to compare two experiments to solve for the exponent. And you can end up with fractions. So always compare two reaction experiments, but put the bigger number on top so that you avoid having fractions. Because for some reason, you guys are better with 4 to 1 rather than 1/4 to 1. So, pick 2. Pick 2. Which 2 do you want to pick?
1 and 3.
1 and 3. Which one's bigger? 3. So we're going to put 3 on top. So what we're going to do is we're going to compare 3 to 1. And then you fill in the data from the experiment. So the rate for 3 is 9.9 times 10 to the negative 6 mole per liter per second is equal to some constant K times the concentration to the exponent M. All over the information from the first experiment. So the rate here was 3.3 times 10 to the negative 6 mole per liter per second is equal to some constant K times the concentration to some exponent M. These units are going to cancel because they're on the top and the bottom. K is a constant. It's the same value, so it's going to cancel. So what you can do then is, what is 9.9 times 10 to the negative 6 divided by 3.3 times 10 to the negative 6? 3. So 3 is equal to, and you can change the right-hand side. What is 0.45 divided by 0.15? 3. So 3 is equal to 3 to the M. What is M? 1. So it's first order with respect to our reactant. So R is equal to K SO2 Cl2 to the 1.
So we
Yep.
would we have to use logarithms if it's not as straightforward as something we don't want to guess and check?
Yeah. But we're not gonna. I'm gonna give you nice numbers. Okay, so now we're gonna solve for K. Yep.
We would have done like any of the other ones, we would all.
So we're going to take the data from 1. 3.3 mole per liter per second is equal to K 0.150 mole per liter to the exponent 1. So if we want to isolate K, we're going to divide both sides by 0.15 mole per liter.
Is it supposed to be 10 to the negative 6?
Times 10 to the negative 6. Thanks, Samin. Times 10 to the negative 6, sorry. So take 3.3 times 10 to the negative 6 divide by 0.150 mole per liter. Is this going to be a big number or a little number? Big? Be big if it was. 3.3 times 10 to the negative 6 mole per liter per second divided by mole per liter. Big number? Small number.
Oh, I did it wrong one.
2.2 times 10 to the negative 5.
2.2
Yeah,
times 10 to the negative
5.
5. Now, what are my units?
Seconds?
No.
Where's the,
I got no clue then.
We have on the top moles, moles per liter per second. We divide by moles per liter, which is the same thing as multiplying by liters over moles.
So it's 1/2.
1 over seconds. So seconds to the negative 1 or 1 over seconds. This is where I told you we're going to start getting some weird units. All first order reactions, your K unit will be 1 over seconds. So this tells you, that's a very small number. This does not go very quickly. Does not go very quickly. That's a very small number. That's your basic rate law expression right there. That's a mark. So now, the last time we did it, our constant K's change. You've got to get it so that you're only looking at one factor that changes. To see how one change affects the rate, you have to keep everything else constant. So if you are going to solve for the exponent m, you have to pick 2 trials where h2 is the same. To solve for n, you have to pick 2 trials where the concentration of NO is the same, because you want constants so that they cancel. So if we're going to do m first, which 2 trials do we use? 3 and 2, because hydrogen will cancel, because it'll be on the top and the bottom. Which one do you want on the top? 2 or 3? 3. So we're going to do 3 to 2. So we have 8.8 times 10 to the negative 5 mole per liter per second equals 0.8 mole per liter to some exponent m times 0.2 to the n, all over 2.2 times 10 to the negative 5 0.4 0.2. Oh, I forgot my K. So now you're going to get rid of anything that's on the top and the bottom. So what your units are going to go for moles per liter for rates. 0.2 to the n, gone. So you're left with 8.8 times 10 to the negative 5 divided by 2.2, which is 0.4 is equal to, what's 0.8 divided by 0.4? 2 to the m. What is m?
2.
M is 2. So it's second order. Second order with respect to NO. And now you're going to repeat for hydrogen. So you have to pick two rates where NO is constant. Brianna? 1 and 2. Which one do you want on top? So we're going to do 2 to 1. 2.2 times 10 to the negative 5. 1.1 times 10 to the negative 5. Now, some of you will see that eventually you just have to write this. These will cancel, so you won't even write them. You're just going to put the concentrations and then the exponents. Right? You can do that. I didn't do it yet because some people don't see that right away. So, the k's are going to cancel. The 0.4 to the m is going to cancel. 2.2 divided by 1.1. So 2 is equal to 0.2 divided by 1. Sorry, 0.2 divided by 0.1. 2. So what is n?
1.
N is 1. So it's first order with respect to H2. So if you want, you can skip writing out this whole thing. Just do the rates to the concentrations that change because the rest of it you know cancel. Are you okay? All right, so rate then is equal to K NO to the second order, H2 to the first order. A lot of times, this is where mistakes are made and you put the wrong exponent with the wrong reactant. You switch them. So be careful that you don't do that. Now, take one experiment, plug it in, solve for K. Our rate is moles per liter per second. But over on the other side, we had moles squared over liters squared times mole over liters. So we're on the right-hand side, you end up with moles cubed over liters cubed. So then you've got moles per liter per second divided by moles cubed over liters cubed, which is the exact same thing as moles per liter per second times liters cubed over moles cubed. Liters squared, moles squared per second. You are going to get weird units. Does that make sense?
What? Okay. It reminds me a little bit.
Did you get this part?
Okay, you applied, okay.
Because you have to do the math, same math to your units as you did to your numbers. So all your Ks are gonna be worth 2 marks. 1 mark for the number, 1 mark for the unit.
So finding out what the units are and then finding out what the numbers are, like 2 separate.
Yeah. Because some of you just give up. You're like, I don't know.
Yeah.
I'm gonna throw down some letters and hope that they, yeah. Be methodical, whatever you did, so look at the overall order. Those are your exponents on this side, right? So this side will end up, it's 3rd order overall, so it's gonna be moles cubed over liters cubed. You're dividing by that, so you multiply by the inverse, and you just cancel.
Why wouldn't it be seconds per mole squared?
Seconds never ends up on top.
No, but like on the bottom, 'cause you have moles squared by seconds, but you have the seconds on the left. You just switch over the seconds to the right side. But you see the mole squared on the bottom, and then you have times per second. Per seconds on the left.
Do you want to put seconds moles squared?
Yeah.
Yeah, you can do that if you want.
No, okay.
Yeah. It's just weird.